Enggak, gua tempel-tempel terus kan.
Gak tahu.
No, season 5 is ongoing.
Oh,
Season 5 is ongoing.
So after
No, that's season 4.
Beliau is what do you use? Yamaha TG, Yamaha TG, Yamaha Kuasa.
Wah,
Ada soundphone komponen beliau. Pak use stop.
that's only because. No, Valero.
Ada papinya.
Pretest kan nggak dinilai.
Already, my mom has jam 10 udah selesai.
Oh, five episode. I haven't finished the last one. The last one. The last one, the guy got season 5.
Which one?
The last episode.
Only 2%. No,
2% died.
no, 4. Total 4, but there's only from the main cast only 2 of them. The other 2,
I think they updated it. What happened?
yeah.
Terima kasih.
You care the name. Apa sih?
Nanti barengan yang habis lagi. Pokoknya per 2 kali collection baru quiz.
Tapi kemarin kalau polisi kok
Kan dia sebenarnya
Prominence.
iya, itu cuma ada yang dua cuma ada dua kan soal antara dua itu. Kan kemarin
kemarin 2. James tuh ngebahas 2 dia. Dua yang pertama itu yang cuman dia ngukur itunya apa sih chain apa yang dipakai. Kalau di yang kedua dia ngukur chain terus sama gearnya panjangnya ukurannya tidak. Palingan yang masuk quiz yang sama ukuran sama nggak mungkin dia cuma ya berapa horsepower ini apa berapa putaran chain apa yang dipakai itu mah gampang banget. Orang dia aja bilang yang diambil mau nilai terendah, masa mau dikasih yang gitu? Empat kali quiz berarti besok ketiga, terus yang terakhir berarti linear.
Yeah, what premium weekday, what premium weekend, Saturday is.
Short rolling, gears, chain. Oh spring juga belum? Spring fastener belum, tiba-tiba udah linear motor. Linear motor. Motor sizing.
If you like premium, you can touch lots of no premium, you cannot touch. Right, Michael? You need to have premium access to touch.
Premium access to touch.
Oh yeah, yesterday I forgot to tell you. For my X. Yeah, you say you want to take the previous X, the previous second. So this one, so many X. Yeah. So before the first X is toxic, yeah, one, two. After that, the second one, she got like for us, it's normal.
Iya, 14.
kan ini dikerja
Ini udah jam. Ini udah jam. Ini tanda tangan.
harga paket banget tuh ya.
Oh juga. Oh gitu.
Yeah, so
Tara. Tara.
yes. Phase 1 is all phase 2. Phase 2. Ayo, Pak. Ah? Ya. Stop.
Dasar gue lu pakai tiket
Always want to that, so that talking.
tiba-tiba Justin Elroy Medusa anjing.
She has a lot of siblings.
Oh sibling has come.
Sini. Password aku nggak apa?
Udah, masukin aja dulu.
Aku lama lu. Berapa tahun lalu? Hah? Lamanya berapa tahun lalu? Lu masih kayak bocil nggak di pokoknya? Ya.
What do you mean?
5 tahun lalu.
No, they would be the one that I don't have it.
Tapi 2007 itu isu 2020.
No, it's
Oke.
others.
Hah?
For me, I
Isu 2020, habisnya 2027.
was one of the last time.
Kok 7 tahun?
Lo nggak tahu?
Pas waktu ini, the last time.
Hijau.
Pilihannya 5, 10, dia 7. Ambil tengah.
Morning. Mungkin masih baik kali itu. Nanti aja.
2022 kali. Enggak ngisu. 2020. Kok isu?
You guys done the pre-test?
Yes.
Yeah. Alright.
Hah? Oh, what's the point for me? Oh shit. The higher the CC, the expensive
Attendance, guys. So next Tuesday will be the quiz for belts and chains. So today we're doing linear motion power screws, right? That's what the pretest that you did.
Linear.
Okay, Rayfan Alonso. Rayfan. Okay. All right. So sorry for a little late. I cannot find my notes, but I said something good enough. Okay, so we are discussing power screws and linear motion. Power screws are everywhere actually. In fact, the invention of threads, by thread I mean the helical, right? So the notion of you can put a thread and they engage with the female side of it and it becomes an assembly. It actually starts from this application because before you can make all these fine threads and lathe and everything, there is the notion of you can create a force multiplier, right? Think about the hydraulic jack, not hydraulic, sorry, the screw jack on your car. You rotate this and it pulls these two together and it lifts that up, right? The press is maybe 1,000-year-old technology. You can rotate and actually create something like 10 times your power by having this thread. So power screws is one of the oldest kinematics, and it gives you a lot of advantage, a lot of mechanical advantage, right? You can clamp something really tight with a small force. Of course, this kind of falls into the gears, belts, and chain power transmission. This is in a way a power transmission too. The difference, I mean, you can think of it as a type of gear, right? So what happens when you rotate? It moves linearly. So you manipulate torque, so you get torque multiplier at the expense of speed, right? You want to race the car, you rotate this, it's very light, so you get the torque advantage. Torque, even though it now translates to linear motion, but you got the torque advantage at the expense of velocity. So you rotate this 10 times, and this thing goes up like a few centimeters, right? You travel a lot. Your hand travels a lot. But this travels just a little bit. Conservation of energy. Cannot cheat. So you want torque, you sacrifice speed. You want speed, you sacrifice torque. So in the same way, you have a lot of displacement here, but a tiny displacement here. A lot of displacement here, a tiny displacement here. And in exchange, you got your force multiplier. The difference with power screw then, on top of gears, belts, and chain, is that it converts rotation into linear motion. And sometimes you can also do this for speed, and we'll look at linear motion systems with in the industrial automation. So sometimes you want force, sometimes you actually want speed, and you can accomplish this in a very fast way because motors can rotate very fast. So let's take a look at the applications first, so you have an idea what we're talking about before we do some calculations. Let's see. Yeah, let's look at this. It's a bit long, so I'll skip some of it.
And how they work. I hope you've had an opportunity to watch. Now that we've learned about motion control.
So here we will have a preview of the system. Maybe not simply the linear motion screw, but together as a system with motors. But this is ubiquitous, and this is everywhere in industrial automation.
Motors, we can begin to apply this knowledge towards motion control application. In this lesson, we discuss what is linear motion control and a few real-world applications with respect to linear motion, positioning systems, and actuators used with stepper and servo motors. Linear motion control, in part, demands much on the actuator, and the linear actuator covers a broad range of products. A linear actuator is a mechanical device that converts energy, such as the power from air, electricity, or liquid, to create motion in a straight line, and it may be used to apply a force. In this lesson, we will focus on how the electrical mechanical aspects of linear motion control are applied when using stepper or servo motors. If you love our video, Sway, motion is an area of motion control encompassing several technologies.
Okay, before we continue, I want to explain a little bit on the mechanics of this. You got the motor, you got the coupler. You know, we learned about all this, right? The screw itself has to be suspended on bearing, right? Because otherwise, I mean, you're going to have a lot of friction. So bearing here, bearing there. So this becomes like basically a shaft that rotates, but with lead screws, with threads, right? Helical threads. And this is called the carrier. The carrier actually has a nut inside that goes back and forth.
Including linear motors, linear actuators, and linear rolling guides and bearings. Linear control systems and actuators are used in industrial automation and machinery, machine tools, computer peripherals such as disk drives and printers, home automation, packaging, assembly, print and machine.
Printers use this a lot.
Package computer peripherals such as disk drives and printers.
If you own an inkjet printer, you notice how the cartridge goes left and right. So that's linear motion because obviously, again, most actuators are rotary, right? So you have to have a way to convert from rotary into linear very fast and very accurate too. So you got belts systems, you got linear systems.
Home automation, packaging, assembly, medical imaging and diagnostics, electronic manufacturing, industrial test and inspection, and robotics applications.
And who here have gone through MRI scan? None of you? Okay, that tells me about age. In an MRI table, you are basically moved into the magnetic resonance imaging. Those of you who is claustrophobic, fear of a confined space. It's very small. You felt like you are in a tube, and so the table moves just a tiny bit at a time because, like I was having an MRI for my neck pain, and basically the imaging takes slices of my bone, right, and the sendi apa sih? Ligaments, right. So it takes slices at a time. So when I lay down, it moves my body like 0 point something millimeters at a time, right? Using linear screws, linear motion. Very precise one too, right? Heavy but precision. So explains why it's so expensive.
Linear drives move the carriage to the desired positions. The most common drive technologies are ball screw drives, lead screw drives, and belt drives. Linear motion control system configurations, including the number of axes of motion, is often the first factor that needs careful thought. The most common are two-axis, X and Y configurations. The less complex single-axis applications and three-axis configurations.
So something like this is called a gantry system or a Cartesian robot, right? You have an XY, and the XY system is usually linear motion.
Are also possible. Many factors need careful consideration when selecting a suitable linear motion control system for a single-axis, two-axis systems include the directly and required waiter, the design or the doing to friction of that object needs to be overcome. Knowing the mass of an object to be moved and its center of gravity as it moves relative to a coordinate point on each axis must also be calculated to determine the force requirement. This calculation needs careful consideration so that the moment loads or the turning effect of a force at multiple points in the system can be established.
So what determines what determines the force needed, the motor sizing on this case? What will be the factors that you calculate?
The speed,
Of course, the speed and
the weight,
the mass that you're moving, right? Mass, force equals mass times acceleration. So how fast do you need it accelerate from 0 to something, right? To the whatever speed you want this to travel on. And that acceleration multiplied by the mass will be the force required. The force required can be translated to torque, which we're going to do. Okay? So force and speed, torque and RPM. That translates to the motor requirement.
In the system can be established. Next, you'll need to determine the speed on how fast in millimeters per second or inches per second the actuator will need to move. Determining the speed combined with the force will give you the mechanical power required and how powerful the motor must be.
Okay, force times speed is basically mechanical power. In rotational terms, force is torque and speed is RPM. Okay, so torque times RPM is horsepower, with some conversion ratios.
Traverse speeds and traverse times are somewhat limited with ball screw drives. Ball screw actuators typically have a maximum speed of 3 meters per second.
So this is a ball screw. We'll take a look at more videos to describe this. You basically have balls like you have in ball bearings, okay? And as this rotates and this translates, the ball elements actually rotate. So it recirculates. This one is basically, when it exits here, it returns the ball here. And so it's kind of spins and recirculates. And it has to be lubricated, obviously. This is called a ball screw.
And for belt drive actuators, the maximum speed is around 8 to 9 meters per second.
So this is faster. Anybody knows why or make a guess? For the same motor, a belt system like in your 3D printer versus a ball screw, this is faster than that. Who wants to tell me why? Huh? No, it's not the friction. Look at the kinematics. Look at the torque and speed trade-off. This is a mistaken animation, by the way. I mean, you wouldn't have it like this, right? Unless you have a warp drive. But in most cases, the motor is actually like this.
Yeah.
So, in a timing belt drive, this is the linear motion, okay? So, the motor rotates a pulley. So if this is the motor, it rotates a pulley like this. This is the radius. Compare this with a motor, sideways, coupler. This is a screw drive with a carrier that moves left and right. This has a belt, and whatever is on here moves back and forth. Look at how much you get for one rotation of motor. Okay? Compare this versus this. Tell me about it in your own words. Okay, in this situation, you move more, right? In here, in one rotation, you only move one lead. We'll talk about lead soon, but yeah, for a single thread, you move 8 pitch, that much. Here, one rotation, you move that much, right?
Yeah.
The circumference. What does that tell you? So one rotation of this, you get one circumference. One rotation of this, you only get this much travel. So for the same RPM, let's say I have 100 RPM here, 100 RPM here, then this one, you're gonna move how much? On this 100 the circumference, right?
Yeah.
Over here, 100 RPM for 100 rotation, you get 100 of the pitch. So no comparison. So this is why this is much, much faster. But conservation of energy, if you can go fast, meaning the torque is low, right? Or the force is low, the linear force.
The highest acceleration of any linear motion control actuator is around 40 meters per second. However, typical accelerations are much less than this, often between 0.5 meters per second and 5 meters per second. Deceleration is also important, especially if emergency stops are required. You'll need to define how far your load or actuator needs to travel. This is known as the stroke length. Many actuators come in standard sizes, It's best to choose an actuator close in size to your requirements versus having a custom actuator built to save cost. Knowing the total stroke length for each axis is critical when specifying your system requirement and will help in determining the correct type of linear motion control drive system. With ball screw linear actuators, for example, the stroke length is limited to the length of the ball screw itself. Therefore, maximum stroke lengths tend to be around 3 meters.
Okay, 3 meters is already pretty long. 3 meters is about the height from the floor to the ceiling. You know, having a lead screw that long is pretty long, okay? And you'll run into so many other difficulties in like deflection, things like that once you go beyond 3 meters.
But with belt-driven systems, there are no such restrictions, and so stroke length can be higher than this, up to as much as 20 meters if required.
20 meters is pretty long. This room, that is probably like 12 meters or 15. Yeah, 12, maybe 12. So 20 meters is like almost double the length of this room. Now, the belts and all that might need some, support, but that's not a problem. We can arrange that, but it can be pretty long. And so, with this being fast, this is one potential to actually shoot an object pretty fast, pretty far.
If linear motors are specified, the stroke length is unlimited, normally around 10 meters. In addition, you will need to determine lifetime requirements or the duty cycle. Duty cycle is defined in how often the actuator will operate and how much time will elapse between movements. Duty cycle is based on the number of expected repetitions per unit of time in hours per day, minutes per hour, and/or strokes per minute.
Okay, I like to discuss duty cycles because it's an important concept for us engineers, especially when you design industrial machines. Now, duty cycle is how often you use something compared to not being used, right? So, what's the duty cycle of your car if you drive a car here? What would be a typical duty cycle of a car? A passenger car, if you ride it to campus and back every day.
2 to 3 hours.
Okay, 2 to 3 hours per day. So what would be the percent?
35%. It's like 3 out of
3 out of
24. Yeah,
3 out of 24. Okay, because 0 is 0% duty cycle. 24 hours will be 100%. That's what duty cycle means. Have I talked about duty cycle before? No? Okay. Alright, so 100% duty cycle means you use it all the time. Okay? That means 24 hours a day, 7 days a week, 365 days a year. That's what 100% duty cycle means. So, if you drive 2 hours per day, this is how much percent? 2 hours out of 24 hours, right? So 2 divided by 24. Okay, whatever that percent is. Easier number. 3 will be 3/8. Is it? 1/8. Okay, so 12.5%. So that's what duty cycle means. You can see your car duty cycle is pretty low, actually, if you think about it. In fact, it might not be designed for 100% duty cycle, especially gasoline cars. Now, diesel engines are different. This is why trucks use diesel engines, because diesel engines are designed to survive 100% duty cycle. This is why generator sets, like to generate electricity in emergency, they are diesel engines, not gasoline engines. The ones you can buy in Ace Hardware is not gasoline engines, but the one in industry or for this building, for example, every office building like this will have a generator set at the basement. If the electricity cut off, then it survives on this generator set. It can operate 100% until the diesel oil runs out. So that's duty cycle, right? Duty cycle makes a difference because I mean I digress a bit here to other topics, but this is the difference between residential machines and commercial machines. Your washing machines, for example, what's the duty cycle? How often do you wash? Once a month? How often do you wash your clothes? Once a week? You wash every day? Wow. Okay. So let's say you use your washing machine twice a week. Typical. What would that duty cycle be? So one cycle of the washing machine is what? 45 minutes? Yeah? So 45 minutes twice a week. What's the duty cycle? What's the duty cycle? So 2 times 45 minutes divided by, this is per week, right? Weekly. So what will be the denominator? 24 hours, 7 days, right? Times 60 minutes. So, quick math, what would that be? So 2 times 45 divided by this number.
0.0089.
0.0089.
8
8.9%. You sure? I expect it to be lower than that. 0 point? Oh, 0089.
0.8.
Exactly. Pretty low. Now imagine if this same washing machine is used for a commercial laundry, let's say in a hotel, washing like 100 rooms full of towels and bed sheets and running like 8 hours a day. So you go from, this is 3 hours per day, 8 hours per day is what? 8 divided by 24? What is that? 1 over 3, 33%, right? So you go from 0.8% to 33%. That's a lot. And a friend of mine told me that one friend of his used residential washing machines, operated 24/7, and it broke in like 3 months. Maybe 2 weeks, I don't know. But this is very significant. You see that a lot of your devices are not designed to do 100% duty cycle. A lot of it. Even your laptop. If you run it 24/7, then you'll start to see a difference in 2 years. Thermal stresses and all that. Anyways, so duty cycle. Now let's talk about this. And duty cycle matters a lot because these things operate many times, 8 hours a day minimum, if not 3 shifts, meaning 24 hours a day. Industrial machineries, right? Right? So now, if I travel from A to B using this ball screw, right? So I'm at A. Let's say I am here like 2 seconds. Because you're doing assembly, right? You're loading something, they put a screw on the product. You travel here for like 0.5 seconds, and then you are here for 1 second. So you wait stationary for 2 seconds, moving for 0.5 seconds, stationary for 1 second, and then return to A. What is the duty cycle of this motor? So it's at rest at A, at point A. It is at rest at point B for this much, and then this is the travel, one way. Calculate for me the duty cycle. Wants to give it a shot?
1 second per cycle.
Hmm?
Per cycle, only 1 second.
You go back and forth, right? One cycle is from A to B and back to A, home, back to
Yeah. So the motor only working for 1 second.
Okay, so the motor is working for how long?
1 second.
1 second out of, so basically 0.5 plus 0.5 divided by the cycle time. What is the cycle time?
2 plus 1, 0.5, 1.
2 plus
1.
half
Oh wait, plus 1.
plus 1
Plus half.
plus half, and you're back home. Don't add the 2 seconds again because that belongs to the next cycle, right? So 2 plus 0.5 plus 1 plus 0.5.
How much that?
So that's 1 over 4, 25%. So that's the duty cycle of this arrangement. The longer you're at rest, then the lower the duty cycle. Okay, so that's what duty cycle is, and it does matter.
Cycle times determine the life of a linear motion control system. The repetitive motion of back and forth, or up and down movements, produces friction, and this friction creates wear and tear on the system components. This cycle time, or duty cycle, is critical criteria in determining the operating life on just how long you want your system's investment to last. Accuracy and repeatability are one of the most considered overall for the system, in which may deliver the desired quality or precision required in the system or manufactured end product.
What
If
is
the
the
application,
difference?
for example, is for an
What is the difference between accuracy and repeatability? Hmm? Want to give it a shot? So let's say I shoot an arrow. Is that accurate? Or is it repeatable? It's both. What is this? This is accurate, but not repeatable. Because the average is right. Right? I'm pretty accurate, but not repeatable. What about this? This is repeatable,
Yes, repeatable.
not accurate. Of course, this is what you want. But if you have to choose between this and this, which one do you want?
Accurate and repeatable.
But That's the aim. But let's say you're calibrating your machine, you're setting up your machines. Which one's preferable? This one? Why? Huh? Just move the target? Well, this is what calibration does, right? You basically offset whatever set point is wrong, whatever parameter is wrong. This also is involved in tuning. You want to make it more repeatable, but repeatability is often inherent to the machine design. If the machine is not repeatable to begin with, for example, things are loose, right? Let's say you have a motor, you have, okay, let's say the motor mounting, there are 4 legs here. Let's say the motor mounting is loose. Somebody didn't tighten it right. What would you end up with? This one or this one? The last one, right? Because if the bolts are loose, you just don't know what it's going to do. You know, the first stroke, if I do this, the second stroke is shifted a bit, it shoots, right? So this is often something is wrong or the design itself is not of good quality. But here, usually you have a good machine. You have a good quality machine. But you just have to tune it right, right? I mean, you loosen the bolt, you shift the motor a bit, tighten it back again, and then it'll be repeatable. Okay? So, quality of a machine, especially this linear motion, is often measured in terms of these.
Automated pick-and-place machine, high repeatability and accuracy are most likely required. Typically, the accuracy of a ball screw linear actuator is 0.16 millimeters per meter with repeatability of plus or minus 0.01 millimeters. For belt drive actuators, the accuracy is around 0.5 millimeters per meter with repeatability of plus or minus 0.10 millimeters.
Still pretty good, even though
Other
it's less.
considerations are millimeters per meter drive at 0.01 millimeters.
So ball screws can be up to like 10 microns. That's very, very accurate. Belt drives are less. So belt drives are less, but still can be pretty good. And this comes down to the controls and the calibration. Okay, so yeah.
Positioning systems are used in applications where accuracy and repeatability are more critical. These positioning tables use either an Acme or ball screw as the drive mechanism.
A ball screw has recirculating balls. An Acme linear lead screw does not. An Acme lead screw is just a thread, so it has more friction, but it's cheaper.
Bearings are used to carry the load of the application. Lead screw solutions provide both simple construction and lowest cost. Many electromechanical designs incorporate a lead screw and lead nut, while some use a ball screw and ball nut.
Okay, so this has recirculating ball. This is just a nut, just like a female thread. That's it.
Sir, before you said lead screws is cheaper, sir, but more friction.
Yep.
Cheaper, more friction.
Okay, I have a better video than this one.
On the threads, the direction of motion of the nut will depend on the direction of rotation of the lead screw. Connecting the load to the nut, the motion can be converted to usable linear movement. Ball screw actuators use ball bearings and are more expensive, but provide less friction compared with lead screw actuators. In a ball screw drive, ball bearings travel along the grooves in a threaded shaft and the ball screw, and recirculate through a ball nut. Because bearings share the load, ball screw linear motion drives have relatively high thrust capacity. A ball screw drive combines repeatable motion and a stiff system that handles high forces and moments. Such systems work well in precision positioning applications with high loads and high duty cycles. Planetary
All right. Enough from this video. Let's look at this.
I hope you have been following our lessons on motion control per second
Oh,
and
this
for
one
belt
we
drive
just did. Sorry.
actuator.
Okay.
Thompson has 70 years of application experience using ball screws, lead screws, and trying to pick the right product for the right solution. The ball screw, lead screw, it can be used in the same applications in many instances. The advantages of a ball screw is mainly the efficiency and the predictable life of a ball screw. Typically, we see a ball screw used in industries that need a lot of load or a lot of life, and they're moving heavy either parts or product. For the lead screw, it's a smaller, lighter duty application product. It's highly customizable. You can change leads and sizes and ball nut configurations very quickly and easily, and that's not the case with ball screws. So it works itself very handily for an OEM application that's trying to integrate a product into their machine and be unique. And a lot of people think of a lead screw as a low-cost alternative, and they're going only on cost. Cost is, obviously very important to many customers, but it's not the most critical component. First test we're going to do is just to show the difference between a ball screw and a lead screw and how quiet and smooth the operation is. So we'll run through quickly a little bit.
So you can tell which one will be more noisy. Ball screws.
What makes up each product. Typically a ball screw made up of 3 or 4 different components. Again, you obviously get your screw, a nut, and the difference between a ball screw and lead screw is just the recirculation system. Obviously we have ball bearings in a ball screw, and then it depends on how you design it, whether those ball bearings are circulated inside the nut or externally. This is an inch style ball screw, and it's got an external return system. The balls actually come outside of the nut before they go back in. And the difference between this, obviously, it makes a little bit more noise. Since this one's not a preloaded system, it's not quite as smooth or accurate as what you find in a preloaded system. Lead screw, you can tell the difference in noise. Basically, there is none. Very smooth, very clean motion, very quiet. See, this screw is a lead screw, very small lead, very fine lead. It's about 0.1. Again, no matter what I do, I can't push on this nut and cause it to back drive it out.
Okay, this is the concept of back drivability. Typically, we are having the motor drive the carrier, right? The question is, if I put this in a vertical situation, can the weight on the carrier drive itself back? Right? I mean, if you push this here, can the carrier rotate the motor? If it's a vertical situation, okay, this is the motor, and you have this in car jacks, right, in the shops. We have a screw on both sides, right? So you have these arms that lifts your car. So the motor is like this. The question is, will your car be able to drive back the motor? The answer is, it depends. And we can calculate that. This is called back drivability. Okay, whether it's back drivable or not, whether it's self-locking. Another word for this is self-locking. Okay, so a self-locking screw means that the linear motion cannot create rotation, but the rotation can create linear motion.